哎，你这个文章挂出来了没有啊？好，还没挂出来。
这个文章挂出来了。
挂出来了是吧？
对。
等一下。哦，我搜到过，忘了。7月份是吧？几月份？
对，这个我之前跟你讲过这个文章。
1月份就挂出来了，后来你是在做一些更进一步的是吧？
就是我们第二版就是把第一版很多东西就等于完全重写，就有挺多东西就重新就是用更好的办法就重新证明了一下。
是换了版本，但是文章没变是吧？
文章没变，就只是换了个版本，因为第一版里面我们需要做一个2次覆盖，就是做一个2次的那个 auto cover，但是在新的版本里面我们就不需要做那个。
新版本还没出来，因为老版本1月份。
就是那个后来更新的那个版本里面就我们后来等于把第一版的那个文章就是很多地方就重写了。
我这儿看的是1月份嘛，1月18号嘛。
它是那边应该是有2个版本吧，一个 V1 一个 V2。
V1是去年的了，20年的。
对 V1 去年的，对 V2 呢就是今年更新的。
OK， 那我们开始吧，好吧？
好，
我介绍一下啊。OK。Hello everyone. Today I'm very happy to introduce Professor Hu Yong from Shanghai Jiao Tong University. And today he is going to talk about Noether-Severi inequality and equality for irregular threefolds of general type. Okay, thank you. You can start.
Okay. Thank you. I would like to thank Meng Shen for the introduction and giving me this opportunity to give a talk at the KS. Let me first introduce the geography of smooth minimal surface of general type. Throughout this talk, we walk over complex number field. Okay, now let S be a smooth minimal surface of general type, because S is a compact complex manifold. So S has the following two basic invariants, C1 square and C2 square. And C2S, it is well known that they characterize a minimal surface of general type up to a finite number of families. Here, minimal means that S does not contain any -1 curves. And general type means that the canonical divisor is a big divisor. The first question in the geography is the following one. Now, we know that these two numbers are integers. So the question is, for a pair of integers AB in Z2, when does there exist a minimal surface of general type S with C1 square is equal to A and C2S is equal to B? In fact, the chain invariants cannot be arbitrary. They have to satisfy the following equalities and inequalities. The first one is that C1 square should be larger than 0 and C2 is larger than 0. C1 square is larger than 0 because S is minimal and of general type. And the C2S is larger than 0 follows from our, this follows from the Miyaoka-Yau inequality or other approach. This can be proved.
Okay, excuse me. So your C1 square greater than 0 cannot imply that the canonical divisor is big. Is nef, right? It still can
be. We assume that the canonical divisor is nef.
Always nef.
So if C1 square is larger than 0, it must be of general type.
Okay. Yeah. Okay.
The second one is Noether's formula. It says that C1 square plus C2 is equal to 12 chi OS. Here, chi OS is the holomorphic Euler characteristic, and it is an integer. So this means that C1 square plus C2 is divided by 12. And if given C1 square and chi OS, then C2 is determinant. The third one is called Noether inequality. It says that C1 square is larger than or equal to 2 chi OS minus 6. And this inequality is optimal. The last one is called Miyaka-Yau inequality. It says that C1 square is less than or equal to 9 KOS. Moreover, when C1 square is equal to 9 KOS, by Yau's theorem, S is a compact Bohr quotient. It is two-dimensional Bohr quotient. Now, so what happens when this optimal inequality becomes an equality? Let me give you the following definition. Let S be a smooth minimal surface. S is said to be on the knot line if S is of general type and satisfies C1 square is equal to 2 KOS minus 6. Horikawa classified the smooth minimal surface on the knot line. The theorem is the following. Let S be a smooth minimal surface on the knot line. Then the canonical map of S induces a double cover over a rational surface Y. And the minimal resolution of this rational surface Y is either P2 or a Hertzsprung surface. The last one is S is simply connected. This means that the topological fundamental group is trivial. Now I would like to introduce the geography of high dimensional varieties of general type. Let V be a d-dimensional smooth projective variety, and let omega V defined by a determinant of holomorphic cotangent bundle be the canonical line bundle. Because this is a line bundle, so there is a divisor, there is a divisor associated to this line bundle. We denoted it by KV, the corresponding canonical divisor of V. The canonical volume of V is defined as the following number. It is the limit of sup H0 V NKV over ND over D times. It mirrors the growth of genus. When the canonical volume is larger than 0, V is said to be of general type. If V is of general type by BCHM, we can replace V by its minimal model X, provided that the property we are studying is birationally invariant. In particular, we have the following. The canonical volume of V is equal to the canonical volume of X. And when X is minimal, this number is equal to KXD. And because X is minimal, the canonical divisor Kx is a Q-Cartier divisor. So this number is a rational number, is a positive rational number. And we have the following birational invariants. This one is called the geometric genus. This is defined by the dimension of global holomorphic deforms. And the QV is called the irregularity. This is H1VOV. Here OV is the structure sheaf. And the holomorphic Euler characteristic of omega V. This is defined by the following sum. The strategy to study the geography of varieties of genotype is the following. The first step is that we have to find the explicit numerical relations among birational invariants of varieties of genotype. Step 2 is we study the fine classification problem based on these relations. Let me introduce the so-called inequality of knot type. The following theorem is a theorem by Meng Chen and Zhi Jiang, published in 2017. It says that let D be a positive integer, then there exist positive constants AD and BD, such that the inequality of knot type, the canonical volume is larger than or equal to AD PGV minus BD, holds for any smooth projective default V of general type. Here, AD and BD are positive constants and depend only on the dimension D. But this is only a theorem for existence. We don't know the effective number of AD and BD. When D is equal to 2, by the classical Noether inequality, we know that we can take A2 is 2 and BD is 4. And when D is equal to 3, we have the following optimal results. This is proved by Yong Chen, Meng Chen, and Chen Jiang in 2020. The theorem is the following. Let V be a smooth projective threefold of general type, and either the geometric genus of V is less than or equal to 4, or the geometric genus is larger than or equal to 11. Then the following optimal inequality of Noether type holds. The canonical volume is larger than or equal to 4/3, PGV minus 10/3. And this inequality is optimal because of Kobayashi's examples. He constructed an infinite number of examples satisfying the equality. The geometric genus starts from 7, 10, and 13, and so on. An infinite number of examples. Okay, now let me introduce the irregular variety. The definition is the following. Let V be a smooth projective variety. If the irregularity is larger than 0, then V is said to be irregular. If V is irregular, there is a well-defined non-trivial Albanese map from V to the Albanese variety. Here, Albanese variety is defined by this quotient. This is a dual space of global holomorphic one forms, quotient by the first homologic group. This is a Abelian variety and often referred as the Albanese variety of V. Now for this Albanese variety, Albanese map, we have the following Stein factorization of A. Now let V to W to A be the Stein factorization of A. F has connected fibers, and G is a finite morphism from W to its image. Then F is called the Albanese fibration of V, and a fiber of F is called an Albanese fiber. Any questions so far? If no, let me go on. Here is the geography of irregular minimal surface of general type. This is a theorem, maybe much earlier than Bomberi's paper. This may be known before, but you can find it in Bomberi's paper in 1973. It says that let S be an irregular minimal surface of general type. Then we have here, because S is minimal, so Ks square is larger than 0. And the inequality says that Ks square is larger than or equal to and KOS can be 1, 2, 3, can be any positive integers. And when the equality holds, it is classified by Horikawa. Let S be an irregular minimal surface of general type with Ks square is equal to 2 KOS. Then the first statement is that the Albanese map A from S to here B is the image of the Albanese map. We proved that the Albanese map, in fact, is the pencil of curves of genus 2. This means that A is a fibration from S to a curve. The general fiber is a curve, and it is a smooth curve of genus 2. And moreover, the image B is a smooth elliptic curve. This means that the irregularity of S is 1. Then he studied because A from S to B is a tensor of curves of genus 2, you can study the relative canonical map. The second statement is that the relative canonical map of A is a generic finite morphism. So there's no base point for this relative canonical map. From S to TB A lower star omega S, because omega B is trivial. So this is just the relative push forward of the relative dualizing sheaf. And moreover, the third statement is that this generic finite morphism psi S factors through the canonical model of S, and it induces a flat double cover from the canonical map of S to this P1. This one is the P1 bundle of elliptic curve. So this is, in fact, this is a flat double cover. This means that this one is flat and the degree is 2. The last statement is that the fundamental group of S is in fact isomorphic to the fundamental group of B, because B is a smooth elliptic curve. So the fundamental group of S is isomorphic to Z2. Okay, this is the so-called inequality of Noether type. Now I will introduce the Severi inequality. The classical Severi inequality states that let S be an irregular minimal surface of general type. Suppose that S is of maximal Albanese dimension. This S is of maximum Albanese dimension means that the Albanese map from S to A is a generic finite morphism onto its image. So the dimension of the image of S is 2. Then the following optimal inequality holds. Ks squared is larger than or equal to 2 chi omega S. This inequality was first stated in Severi's paper in 1932. Unfortunately, Severi's original proof contained a gap, as pointed out by Catanese in 1983, who posed the inequality as a conjecture, and it was finally proved by Padini in 2005. So this is the so-called Severi inequality. So now the inequality Ks squared is larger than or equal to 2 chi OS. This is because S is a surface, so chi OS is equal to chi omega S. So this inequality we call it is called Noether-Severi inequality, because for irregular minimal surface, because it is both of Severi type and it is of Noether type. So it is natural to ask the following question. The first question is that does there exist an inequality of Noether-Severi type for higher dimensional irregular varieties? The second one is it possible to describe the irregular varieties on the Noether-Severi line? For question 1, there are many works when the Albanese dimension is large. So there are many works by Tong Zhang in 2014 and Baha in 2015. Baha, Padini, Stobino in 2020 and Zhijiang in 2020. For question 2, almost nothing is known. When the dimension of this irregular variety is 3, I have the following inequality of Noether-Severi type. This is the theorem in 2018. Let X be an irregular Gorenstein minimal threefold of general type. Then we have the following optimal inequality. Kx cubed is larger than or equal to 4/3 chi omega x. Here, Gorenstein means that the canonical divisor of X is a Cartier divisor. And the method I proved that this theorem relies heavily on the assumption that X is Gorenstein minimal. So now I state our first mean theorem. Our first mean result is the following. Now let X be a smooth irregular threefold of general type. Then we have the following optimal inequality. The canonical volume of X is larger than or equal to 4/3 chi omega X. So this inequality is the same as this inequality. And this is optimal. Moreover, if the equality holds, then the first statement is that the irregularity of X is 1. And the second irregularity, H2 of X is equal to 0. And we know since Qx is equal to 1, the Albanese map of X is a fibration onto a smooth elliptic curve. So the general Albanese fiber of X is a surface. And we prove that the general Albanese fiber of X is in fact a 1-2 surface. This is a very special surface. I will explain this surface later. The second statement is that all minimal models of X are Gorenstein. So if we run minimal model program for X and we get the minimal model, all the minimal models are Gorenstein. This means that the canonical divisor of the minimal model is Cartier. The third statement is that we compute the topological fundamental group of X. And in fact, the fundamental group of X is isomorphic to the fundamental group of the Albanese map. Since the Albanese variety, because the Albanese variety is a smooth elliptic curve, so this is isomorphic to Z2. Here are some observations. Now let X be a smooth threefold of general type. If chi omega X is less than or equal to 0, then the minimal model of X cannot be Gorenstein. Because if X has a Gorenstein minimal model, then by a result proved by Miałka and Reed, we know that chi omega X must be larger than 0. So if this one is less than or equal to 0, the minimal model cannot be Gorenstein. And if the canonical volume is equal to 4/3 chi omega X, then the minimal model of X is Gorenstein. This follows from our theorem, statement 2. And if the minimal model of X is Gorenstein, then the canonical volume must be a positive even integer. This is a factor. Follows from the Riemann-Roch formula. And if X is an irregular threefold, so if X is an irregular threefold on the Noether-Severi line, this means that the canonical volume of X is equal to 4/3 chi omega X. If this equality holds, then we have chi omega X is divided by 3, and the canonical volume must be divided by 4. So, and in fact, we have examples for chi omega X be 3, 6, 9, and so on. For any 3 n larger than or equal to 1, we have an irregular threefold such that chi omega X is equal to 3n, and the canonical volume is equal to 4n. So so when the irregular threefold is on the Noether-Severi line, there are restrictions on the chi omega X and the canonical volume. Note that there is no similar restriction on chi omega S or irregular surface S on the Noether-Severi line. Here, for surface case, chi omega S can be any positive integers. So this is the difference between surface and threefold. Now I would like to introduce the geometry of 1-2 surface. We say that a smooth projective surface S is a 1-2 surface if the canonical volume of S is equal to 1 and the geometric genus of S is equal to 2. Now let S be a smooth minimal 1-2 surface. Because the geometric genus of S is equal to 2, then the canonical linear system is non-trivial and it induces a map to P1. The fact is that the canonical linear system has a unique base point P. Now let sigma be from S prime to S be the blow up at P. Then the movable part of sigma up star Ks of this linear system is base point free. And it is composed with a rational pencil of curves of genus 2. This means that this linear system induces morphism from S prime to P1. And the general fiber is a smooth curve of genus 2. Now let F from X to B be a minimal fibration over a smooth projective curve B, such that the general fiber F of F is the minimal 1-2 surface. Here, minimal fibration means that X has at the worst 2 factorial terminal singularities, and the canonical divisor is relatively naff. So the general fiber must be a minimal surface. And now we assume that the general fiber is the minimal 1-2 surface. Then the fibration F has the base locus section gamma, whose intersection gamma with F is just the base point of Kf. So this means that the base point of canonical linear system of the general fiber induce a section of this fibration. Now I would like to introduce our theorem 2. It says that let X be the canonical model of a smooth irregular threefold of general type on the Noether-Severi line. This means that the canonical volume of X is equal to 4/3 chi omega X. And the canonical model means that the canonical divisor Kx is ample and X has at worst the canonical singularities. The canonical model of a variety of general type is unique. Now denoted by A from X to B, the Albanese map of X. Recall that by our theorem 1, we know that Qx is equal to 1. And the general Albanese fiber is a 1-2 surface. So B is a smooth elliptic curve, and A is the fibration. General fiber is the 1-2 surface. Our first statement is that the base locus of the relative canonical map of the Albanese fibration A is just the base locus section gamma. So the base locus is just this section gamma. It is easy to see that this section gamma lies in the base locus of this relative canonical map. We proved that the base locus is just this gamma. And we have the following commutative diagram. If we blow up this section gamma, we get X prime. This is the relative canonical map of A. And if we blow up this base section, we get the rational map from X prime to this P1 bundle. And we prove that this F is indeed a morphism. And moreover, this F from X prime to, I denote this surface, this P1 bundle by S. This is a flat family of curves of genus 2. This means that all closed fibers of this F is an integral curve. It's a curve of arithmetic genus 2. So F is flat. The second statement is that if we denote by P from S to B, the natural projection, because S is the P1 bundle. Now we set E be the F lower star OX prime 2E. Here E is the exceptional divisor of pi. Here pi is the blow up of this section. So we have the exceptional divisor E. Then we have the following commutative diagram. Notice that this F is a vibration from X prime to S. So we get to this psi. This is induced by F up star F lower star OX prime 2E to OX prime 2E. And in fact, we prove that this psi is a morphism. And the third statement is that psi from X prime to this PSE, this is a flat double cover with the branch locus D. Here, I forgot to say that we prove that this E is a locally free sheaf of rank 2, and it splits. This is in fact OS direct some natural divisor. So psi is a flat double cover. In fact, this psi is just is the same as the relative canonical map of F. Now the general fiber of F is a curve of genus 2. So this is a morphism, generic finite morphism of degree 2. Because if you restrict to the general fiber, this is just the canonical map of a curve. The statement is that psi from X prime to this PSE. Here PSE is the P1 bundle over S. This is a flat double cover with a branch locus D. D is equal to D1 plus D2. Here D1 does not intersect D2. Moreover, D1 and D2 are explicitly described, and this D1 is in fact a section of this P1 bundle. And D2 is in a linear system, and we described this linear system. So the main result of theorem 2 is just the following. Suppose that X is the canonical model of an irregular threefold on the Noether-Severi line. Then we have the following commutative diagram. Now, we first consider the Albanese fibration. This is the fibration over a smooth elliptic curve. And the general fiber is a 1-2 surface. So there is a natural section called the base locus section. And we blow up this section, we get X prime. And X prime factors through this one. So first we have a P1 bundle over B. This is the surface. We consider the relative canonical map from X to S. And then we consider the relative canonical map of X prime to S. In this case, the general fiber is a curve of genus 2, and it's a smooth curve of genus 2. Now, this relative canonical map induces a flat double cover to a P1 bundle over S. So this X, so conversely, this X can be is just a divisorial contraction of a double cover over 2 tower P1 bundle over Albanese variety of X. So the X can be get from we first have a smooth elliptic curve, and you consider a P1 bundle here S, and you get another P1 bundle over S, and take a double cover, we get X prime, and take a divisorial contraction, we just get the canonical model X. And the examples is constructed in this way. Here are some related results in dimension 3. First result is that Yong-Kai-Chen, de Bach, and Zhijiang have obtained up to 8 covers an explicit description of threefolds X of maximal Abernethy dimension and of general type with chi omega X is equal to 0. When X is of maximal Abernethy dimension, by generic vanishing theorem, we know that chi omega X is larger than or equal to 0. Then Kola asked if we suppose furthermore that X is of general type, is it possible that chi omega X must be larger than 0? Later, maybe Green and Noether-Severi constructed counter examples, and they proved Yong-Kai-Chen and de Bach Zhijiang's result proves that up to 8 covers, Green and Noether-Severi's examples are the unique examples. The second result is by Tongzhang and Baha's result. For threefolds X of maximal Abernethy dimension and of general type, we have the canonical volume is larger than or equal to 12 chi omega X. And based on the work of Baha, Pardini, and Stovino, Zhijiang completely described threefolds X of maximal Abernethy dimension with chi omega X is equal to 1. And by this inequality, we know that the smallest volume is 12. It proves that the canonical model of X is a double cover over a principally polarized abelian threefold A, and the branch locus is D in 2 theta A, where theta A is the theta divisor of A, because A is the principally polarized abelian threefold. So there is a theta divisor on A. Okay, now I will give a sketch of proof of our theorem 1. The proof first by my joint work with Tongzhang in 2021. This is published in 2021. We only need to consider the case when the general Abernethy fiber is a 1-2 surface. When the general Abernethy fiber is not a 1-2 surface, we proved that the canonical volume is larger than or equal to 2 chi omega X. So we only need to consider the case when the general Abernethy fiber is a 1-2 surface. The second step is that we prove that when the general Abernethy fiber is a 1-2 surface, we have the canonical volume is larger than or equal to 4/3 chi omega X plus 2/3 H1 OX minus 1. So this is slightly stronger than the canonical volume is larger than or equal to 4/3 chi omega X, because H1 OX is larger than or equal to 1. So when the equality holds, the canonical volume is equal to 4/3 chi omega X. First, by our previous results, we know that the general Abernethy fiber is a 1-2 surface, because if it is not a 1-2 surface, we have canonical volume for the larger than or equal to 2 chi omega X, which is a contradiction. So the general Abernethy fiber is a 1-2 surface, and by the above inequality, we know that H1 OX is equal to 1, because if this is larger than or equal to 2, this will be larger than 4/3 chi omega X. So we get H1 OX is equal to 1. And then we applying the method of Yong-Kai-Chen, Meng-Chen, and Chen-Jiang in 2020 to the irregular case. We prove that if H2OX is larger than 0, we have the following inequality. The canonical volume of X is larger than or equal to 4/3 PGX minus 1. Because in this case, we have H1 OX is equal to 1. So this one is larger than or equal to 4/3 chi omega X. You see that chi omega X is PG plus QX minus H2OX minus 1. So this is just PG minus H2OX. we assume that H2X is larger than 0. So this one is larger than or equal to 4/3 chi omega x. But we assumed that the canonical volume is equal to 4/3 chi omega x. So this does not hold, which means that H2OX must be 0. Then, by read this Riemann-Roch formula, we have the following number. The L2OX, this is defined by this is equal to H0x 2ks. This is just P2x minus 1/2 the canonical volume of x and minus 3 chi omega x. By the classification of three-dimensional terminal singularities, we know that this number is larger than or equal to 0. And if this number is equal to 0, the minimum model of x must be Gorenstein. And we prove that this number must be 0. Then in the last step, we applying the method of Xiaogang in 1991 to the threefold x. We prove that the fundamental group of x is isomorphic to the fundamental group of the Albanese variety, which is just Z2, because the Albanese variety is a smooth elliptic curve. Okay, this is the proof of our theorem 1. Theorem 2 is proved in the following. First, suppose that x is a canonical model of an irregular threefold on the Noether-Severi line. Now let A from x to B be the Albanese map. By theorem 1, we know that B is a smooth elliptic curve and the general fiber is a 1-2 surface. Now we take a sufficiently ample divisor D on B. The relative canonical map of A is in fact induced by the linear system Kx plus A up star T. So we study this linear system. We first prove that the base locus of this linear system is just the base locus section gamma. Moreover, we prove that this section gamma lies in the smooth locus of x. So gamma does not intersect with the singular locus of x. Then we blow up of x along gamma. Since gamma lies in the smooth locus of x, we know that x prime has at worst canonical singularities, and denoted by E, the exceptional divisor. Then we prove that f from x prime to s, here s is just the P1 bundle to B over B. We prove that this is a flat family of curves of genus 2. Moreover, we prove that every fiber of F is integral, which means that every fiber is irreducible and reduced. And we know that the canonical divisor is invertible, is a Cartier divisor. So every fiber of this fibration is a Gorenstein integral curve. Now we set E be F lower star OX prime 2E. Then we show that E is the locally free sheaf of rank 2, because if you restrict E to every closed, because if we restrict OX prime 2E to every fiber, this is just the canonical sheaf of the fiber. From here, we know that H0 of this sheaf, this is just the arithmetic genus of the curve. This is just 2. So E must be a locally free sheaf, and then we show that psi from x prime to PSE. Now E is the locally free sheaf of rank 2. So PSE is the P1 bundle over S. We show that psi is a flat double cover. Which means that psi is in fact finite and of degree 2. And it is flat. Then we compute the branch locus of psi. And we prove that this locally free sheaf E splits into the direct sum of two line bundles. Moreover, we obtain the explicit description of the corresponding line bundles. Then we finish the proof. Okay. Thank you.
Okay, thank you very much. Any question? Okay, I have several questions. First, you say that you apply the Shao-Gang's result to show that the fundamental group is the same as the fundamental group of the elliptic curve, right?
Yes.
And does it mean that the Sheffield map of the pi1 x2 while the Abernathy map are isomorphic? You prove this, or?
Yes, this is isomorphic.
Okay. Okay, and in your last page of your proof, you say that the push forward, your A push forward of your
you mean this
2E,
one?
I mean.
Oh, yes.
Is rank 2 vector bundle. So can you say a little bit, does it mean that the intersection of E and the fiber is one half? Or?
Yes. If we restrict E to the fiber, this is just a half of the canonical divisor. So 2E restrict to the fiber is just the KC.
It's just a KC, so it is 2, right? It's 2.
Yes. So that if you can compute the H0, this is 2, because it is a Gorenstein curve.
Then you apply the Groth theorem that's to say that the push forward is locally free?
Yes. Here F is flat.
Okay. But I remember it's locally free of rank 3 or rank 2.
Rank 2. Because the curve is genus 2.
Okay.
So H0 KC is just the arithmetic genus PAC. This is 2.
Okay, because I remember for ruled surface, okay, let me move to the next question. So do you have any restriction on the base S? Because your S is a ruled surface over an elliptic curve, right?
Yes.
So it can be arbitrary, or?
You mean A lower star omega X?
Yeah, it can be trivial, or it can be arbitrary. Or...
It cannot be trivial, because the degree of this one is just chi omega X, and by our assumption, we know that the canonical volume is equal to 4/3 chi omega X.
Okay.
And chi omega X is divided by 3. So the degree of this one is divided by 3.
Divided by 3.
Yes, divided by 3, and it is a Neff vector bundle.
Okay. I see. Okay, thank you. So any more questions?
Oh, hello, Professor Kung.
Yeah.
Hello, Professor Kung. I just
a long time no see. So yeah, it's nice talk. And then, so how are you in Shanghai?
It's fine in Shanghai.
Okay, so you settled down there?
Yes.
It's good. Yeah.